In the series Advanced Mathematics, we are going to start our lecture 3 of the chapter Vector Calculus, and in this lecture we will talk about the basic definitions and some concepts related to divergence and curve. So, we start this chapter with the definition of divergence. So, we are saying suppose a continuous differentiable vector function f vector, it is given to us, its value we are saying it is f1 I cap plus f2 j cap plus f3 k cap. So, divergence of f, that is equal to del vector dot f vector. So, the answer we obtain, the value of del we know it is del by del x I cap plus j cap into del by del y plus k cap into del by del z, and its dot product with f vector. So, answer we obtain, this is del f1 by del x plus del f2 by del y plus del f3 by del z. So, this value we are saying, this is the definition of divergence of f vector. So, clearly this is a scalar quantity because it is dot product over here. So, the answer we are getting, it is a scalar. So, divergence of f vector, it is a scalar quantity. Now, the next topic we have is the physical interpretation of divergence. So, suppose we are saying that we have a fluid and it is moving with a velocity of v vector, it is given by vx I cap plus vy j cap plus vz k cap. Now, we consider a small element over here, this is the parallelopiped we are considering, and in the direction of y axis, suppose the fluid that is moving over here, we are talking about this is the fluid, the component of the fluid, this moving towards y axis, we are saying it has the velocity vy on this face, and the area of this face, it is delta x into delta z. So, the amount of fluid entering inside this parallelopiped, it is given by vy delta x into delta z. Next, we are considering the fluid is coming out of this side of the parallelopiped, this face of the parallelopiped, and the velocity with which it is coming out, the velocity with which it is coming out, it is vy plus curly vy by curly y into delta y, whatever the change in y is there. So, the amount of fluid leaving from this side, that will be given by into delta x into delta z. The area is same, it is a parallelopiped we are saying. So, what we obtain from these two results is, this is the amount or volume of fluid entering, this is the volume of fluid leaving from this side. So, the change in volume, it is given by curly vy by curly y into delta y delta x delta z. Similarly, if we write the similar kind of thing for the x direction, we are talking about the x direction, we obtain it is curly vx by curly x delta y delta z, and similarly for the z direction. So, we are saying the change in the fluid, the total change in the volume of the fluid, it is given by sum of all these values. So, sum of all these values we obtain, it is curly vx by curly x plus curly vy by curly y plus curly vz by curly z into delta x delta y delta z. Now, this term we are saying, this is basically the divergence of v vector. So, what we have obtained from this is, what this term is giving us, we are saying this total value, it is total decrease in amount of fluid inside the parallelopiped per unit time. This quantity delta x into delta y into delta z, this gives us the volume of the fluid. So, what we are getting is that this divergence of v vector, this is rate at which the fluid is diverging from a point per unit volume, and this amount, this divergence of v, this is called the fluid flux. And in case we are considering this v as the electric field, then that is called the electric flux. If this is electric field, it is called the electric flux. So, it is basically the rate at which the fluid or the electric field is diverging from a point per unit volume. This is the physical meaning of divergence. So, we have further, if the divergence is 0 for a particular fluid, we are saying if divergence of v vector is equal to 0, what this thing means is that the amount of fluid that is entering, that is equal to the amount of fluid that is leaving. So, in that case the fluid is called incompressible. The fluid is called incompressible fluid. And in hydromechanics, this equation is known as equation of continuity of incompressible fluid. This equation, divergence of v vector is equal to 0, this is called the equation of continuity. Next we have the definition, it is the solenoidal vector function or source field and sink field. So, we are saying we have a vector function f vector, it is said to be solenoidal if divergence of f vector is equal to 0, and it is called source field, this is called source field if divergence of f vector is greater than 0. It is called sink field, this is called sink field if the divergence of f vector is less than 0. So, these are the three definitions that we have. We are saying it is solenoidal when divergence is 0, it is called source field if divergence is positive, and sink if divergence is negative. So, the divergence is positive means that the amount of fluid that is entering, that has basically increased. When we are talking about the sink, we are saying the amount of fluid that is entering, that is basically decreased. So, we are saying that this is acting as a sink and this is acting as a source. And when divergence of f is 0, it means the amount of fluid that is entering and leaving, it is equal. So, these are the three definitions that we have. The next definition we have over here, it is curl. So, curl is, again we are considering a continuous differentiable vector point function f vector. So, curl of f vector, it is defined as del vector cross f vector. When we are talking about the gradient, we were having the dot product over here, now we are having the cross product. So, the answer in this case, that will be a vector quantity. So, we are saying the curl of f vector is a vector quantity, whereas divergence of f vector, that was del vector dot f vector, that is a scalar quantity. So, we now are if we have to calculate the value of this, curl of f vector is curl of f vector, that is equal to I cap curly by curly x plus j cap curly by curly y plus k cap curly by curly z, and cross product with f1 I cap plus f2 j cap plus f3 k cap. So, the answer we obtain, it is I cap, j cap, k cap, determinant of, then we have it is curly by curly x, curly by curly y, curly by curly z. This is f1, f2, f3. So, this is the value of curl of f vector. This is how we can calculate the value of curl of f vector. Next we have is the physical interpretation of curl. So, suppose we are saying that a body, a rigid body, we are saying it is rotating about a fixed axis through O. This is some rigid body, this is some fixed axis which is passing through O, and this body, it is rotating with the angular velocity omega vector. Then the velocity of any particle PR, we are considering any particle PR vector, and we are talking about the velocity of this particle. It is given by V vector is equal to omega vector cross R vector. Now if we calculate the value of curl of V vector, the answer we obtain, it is sigma I cap cross curly by curly x V vector. Now omega vector, it is constant over here, so we obtain this is equal to sigma I cap cross, we have omega vector cross R vector, so we can write it is omega vector cross curly R vector by curly x. In place of V vector we are writing this value. So this is equal to sigma I cap cross omega vector cross. Now if we calculate the value of curly R vector by curly x, the answer we obtain, it is I cap. This is scalar vector triple product. So the value we are getting, it is sigma I cap dot I cap into omega vector minus I cap dot omega vector into I cap. So the answer we are getting, it is sigma omega vector minus the value for this I dot omega 1, we have omega vector, that is omega 1. So we are getting it is sigma omega 1 I cap. We are saying this omega vector, it comes out, we are getting sigma 1 minus this value we get, it is omega vector. So it is 3 times omega vector minus omega vector. The answer we obtain, it is 2 times omega vector. So we are saying the curl of the velocity vector is twice the angular velocity of rotation at any point. So in general we are saying the curl of any vector point function, it gives us the measure of the twice the angular velocity at any point of the vector field, and because of this it is called the vorticity of V vector. This curl of V vector, it is also called the vorticity of V vector. Now if we have the value of curl of F vector that is equal to 0, then we obtain that the vector field we are saying it is irrotational. Then that field, it is irrotational, there is no rotation over here, and in that case we are saying the field, it is conservative. This is the definitions that we have. We can call when curl of F is equal to 0, we can say it is irrotational, or we call it is conservative field. And if curl of F is not equal to 0, we are saying curl of F vector is not equal to 0, in that case it is called rotational. It is called rotational. Next we have is potential of an irrotational vector field. So we are talking about, let F vector, it is an irrotational vector field. So this implies us that curl of F vector is equal to 0. So we are saying that for any scalar function phi, we have curl of gradient of phi that is equal to sigma I cap cross curly by curly x into gradient of phi. So this value is equal to sigma I cap cross curly by curly x into gradient of phi is I cap curly phi by curly x plus j cap curly phi by curly y plus k cap curly phi by curly z. We are writing this is equal to sigma I cap cross. Now the terms we have, it is I cap curly 2 phi by curly x square plus j cap curly 2 phi by curly x curly y plus k cap curly 2 phi by curly x curly z. Now if we take this cross product over here, we obtain this is sigma I cross I, that will be 0. The next term we will obtain, it is k cap curly 2 phi by curly x curly y Next, I cross k, that will be equal to minus j. So, we are writing it is minus sigma j cap curly 2 phi by curly x curly z. So, again if we write in terms of I, we are having this k over here, it is sum, this is sum, this is j over here, we can write this is sum over I cap, we are having del 2 phi over, it is k, then it is xy. So, we obtain over here curly y curly z minus sigma I cap, we are writing it is curly square phi by this, these two values will change to curly z by curly y, and this value comes out to be equal to 0. We are considering the function phi such that these partial derivative, these are equal. So, all the conditions for the equality of these two, this phi is satisfying. So, we are saying that this net value we obtain, it is equal to 0. So, what we have seen, that there exists a function phi such that f vector is equal to gradient of phi, and this phi is called the scalar potential of f vector. How we have, I am again repeating this, how we have started the proof. We are saying that if f vector is irrotational, then curl of f vector is 0. So, we have shown that if we calculate the value of curl of gradient of phi, that is equal to 0. It means we are saying that if f vector is equal to gradient of phi, then the curl of f vector will be equal to 0. So, we are saying corresponding to each f vector which is irrotational, we can find a phi, and this phi we are calculating over here. This is called the scalar potential of the f vector. So, what we have obtained, that f vector is irrotational, and to calculate the phi, that is the scalar potential corresponding to this f vector, what we are going to do, we are going to write f vector is equal to del of phi. It means this thing implies us that I cap curly phi by curly x plus j cap curly phi by curly y plus k cap curly phi by curly z, this is equal to f1 I cap plus f2 j cap plus f3 k cap. So, by comparing the coefficients over here, we obtain that curly phi by curly x is equal to f1, curly phi by curly y is equal to f2, and curly phi by curly z is equal to f3. So, if we write the value of d phi, we are writing it is curly phi by curly x dx plus curly phi by curly y dy, we are writing the total derivative, plus curly phi by curly z dz, that is equal to f1 dx plus f2 dy plus f3 dz. And from this relation, by integrating this term, we can obtain the value of phi, that is the potential corresponding to the irrotational field f vector. Next we have is the del applied to point functions. We have certain results over here. These are the 5 results. First is that divergence means we are saying del vector dot gradient of f, that is equal to del square f, and we are proving that this is equal to curly 2f by curly x square plus curly 2f by curly y square plus curly 2f by curly z square. Similarly, if we are calculating curl of gradient of f, it is 0. If we are calculating divergence of curl of f, it is 0. And next we have these two results. Now we are going to prove all these 5 results. So, coming to the first part, we are saying del square f. Del square f means we are talking about curly by curly x I cap plus j cap into curly by curly y plus k cap into curly by curly z dot it is curly f by curly x plus curly f by curly y plus curly f by curly z, because this f we are saying this is a scalar function. So when we do the dot product over here, it is I, j and k over here. When we do the dot product, we obtain it is curly 2f by curly x square plus curly 2f by curly y square plus curly 2f by curly z square, and this operator delta square f, we are saying this delta square operator, this is called the Laplacian operator. This operator, it has a special name, it is called Laplacian operator. As this operator it is called del, this del square it has a special name, it is Laplacian operator. Next, second thing we have to prove is that curl of gradient of f is equal to 0. So we are writing curl means this, gradient of f means we are saying del f. So if we calculate this value, we are saying it is sigma I cap cross curly by curly x, this is the definition of this, and we are taking the cross product with I cap curly f by curly x plus j cap curly f by curly y plus k cap curly f by curly z. Now if we take the product over here, we obtain this is equal to sigma, the product of these first two, I cross I, it is 0, then we have I cross j, it is k cap, and the answer we obtain it is del 2f over del x del y. Then the product of these two we are having it is minus j cap, we have sigma over there, and it is del 2f over del x del z. Again writing the values in terms of I, we are writing I cap curly 2f over curly y curly z minus sigma I cap curly 2f over curly z curly y, and this is equal to 0. This value is equal to 0 because this f function we are saying it is continuously differentiable, we are considering over here. So both these partial derivatives we are saying they are equal. So the answer we obtain in this case it is equal to 0. Next is divergence of curl of f, that is equal to 0. So we are saying del vector dot del vector cross f vector. If we use the scalar triple product over here, we can directly write this is del vector, this is del vector, so the answer is 0. So in place of using that, we are just giving the proof over here. So proof goes like this, we are saying this is sigma I cap cross curly by curly x into I cap cross curly f vector by curly x plus j cap cross curly f vector by curly y plus k cap cross curly f vector by curly z. And these values we are saying, these values these are equal to the scalar triple product, it is I cap curly 2f by curly x square, the sum of terms in this form, then it is plus sum, it is I cap j cap curly 2f by curly x curly y, and last we have it is sum I cap k cap curly 2f vector by curly x curly z. Now if we solve these values, we obtain this is equal to this first term, it is 0, it is I cap over there, this term will be 0. From this second term, the answer we are getting sigma I cap cross j cap dot curly 2f vector by curly x curly y plus sigma I cap cross k cap dot curly 2f vector by curly x curly z. Now I cross j we know it is k cap, and I cross k we know it is minus j cap. So we can write the answers in the form, it is sigma I cap dot curly 2f vector by curly y curly z minus sigma I cap dot curly to f vector by curly z curly y. Again, both these values, these are equal because f vector we are considering it is continuously differentiable function. So, the answer we are getting it is equal to 0. So, we are saying that divergence of curl of f vector is equal to 0. Now, next we have to prove that curl of f vector is equal to gradient of divergence of f vector minus del square f vector. So, we start with this. We are saying the definition of curl we have it is sigma I cap cross curly by curly x, and then we have the curl of f vector, and the value of curl of f vector that we will have it is I cap cross curly f vector by curly x plus j cap cross curly f vector by curly y plus k cap cross curly f vector by curly z. Now, if we take the scalar product, the vector product over here, the vector triple product, we are writing the answer in the form. Look at this term I cap, when it is multiplied over here, we are getting it is sigma I cap cross curly 2f by curly x square plus sigma I cap cross j cap cross curly 2f vector by curly x curly y, and last term we have plus sigma I cap cross k cap cross curly 2f vector by curly x curly z. So, these are the vector triple products that we have. Now, corresponding to this first term, we obtain this is equal to sigma I cap dot curly 2f vector by curly x square I cap minus curly 2f vector by curly x square. In the next term we have I cross j. So, when we will do the dot product over here, the answer will be 0. So, we are left with the term it is sigma. The value we obtain it is I cap dot curly 2f vector by curly x curly y into j cap, and the last term we have it is sigma I cap dot curly 2f vector by curly x curly z into k cap, the second term that will be 0. Now, if we separate all these terms, we obtain this term it is in bracket over here, we are getting it is sigma I cap curly 2f vector by curly x square I cap plus the next term we are writing it is this term. So, it is sigma k cap dot curly 2f vector by curly z curly x into I cap. Next we are writing this term it is sigma I cap into j cap dot curly 2f vector by curly y curly x, and last we have it is minus sigma curly 2f over curly x square. Now, look at this last term. When we take the sum of all these terms, means we are saying sigma curly 2f by x square, then it is by y square, then it is by z. The last term we will obtain it is by z square. So, we are saying that the sum of all these terms that is equal to del square f vector, that is equal to del square f vector, it is minus sign over here, and from all these terms we can take I common. So, we are writing it is sigma I cap into I cap dot curly 2f vector by curly x square plus j cap dot curly 2f vector by curly x curly y plus k cap dot curly 2f vector by curly x curly z, and this term we are saying this is equal to sigma I cap curly by curly x we take common we are left with this I cap dot curly f vector by curly x plus j cap dot curly f vector by curly y plus k cap dot curly f vector by curly z. Look at this term over here. This is the definition of divergence of f. So we are writing this term we have, it is divergence of f, and we are having over here it is I curly by curly x, it means we are saying it is gradient. So the answer we are getting it is in this form, it is gradient of divergence of f vector minus del square f vector. So this is the proof of this result. So in the previous slide we have proved that curl of f vector, that is equal to gradient of divergence of f vector minus del square f vector. So if we shift this term on this side, we obtain this result, that is gradient of divergence of f vector, that is equal to curl of f vector plus del square f vector. Otherwise, if you want to prove this thing as independent proof, so this proof is given over here, you can try this proof at your own. We are saying it is gradient, so gradient is I cap curly by curly x, and this is the definition of divergence of f vector. When these are being operated, we obtain the final answer in this form, that is the required value in this case. So either you can use the previous result to prove this, or this is the independent proof given over here that you can try at your